Hello, we are from Huazhong University of Science and Technology in China, and we'd like to share our work, expanding hyperspherical space for few-shot class-incremental learning. In recent years, the ability for a model to learn continually is gradually attracting attention. Known as class-incremental learning, deep learning models should incrementally expand their knowledge and discriminate new classes. The primary challenge of CIL is catastrophic forgetting, where the performance of the model on old classes decreases significantly when updated with new classes. Besides, collecting and labeling data can be an expensive process, resulting in models that may only be trained on limited new data. This makes the task more challenging, particularly when addressing few-shot inputs in the incremental learning scenario known as few-shot class-incremental learning. To address such problem, ProtoNet introduces the concept of prototypes, which can somewhat alleviate catastrophic forgetting in the case of limited new data. In ProtoNet, the feature extractor is frozen after training on the base session, and the average embedding of each class is obtained to replace the classifier as a prototype. The model discriminates classes based on the similarity, typically cosine similarity, between the embedding of the instances and the prototypes. This approach can maintain a better performance on instances from old classes as only the classifier is updated in the incremental session, and the prototypes of the base session remain unchanged. However, since the extractor is not trained on data from new classes, the embeddings of new classes may be mixed with old ones, resulting in poor discriminability of new classes. Additionally, the overlapping areas of the distributions of the old and new classes not only cause the performance of the model on the new class to degrade, but also the performance of the base session. To address the limitations of ProtoNet, recent advances in the field of FSCIL have sought to design more sparse embedding spaces. FACT proposes forward compatibility and uses multiple virtual prototypes to reserve space for future classes in the embedding space. Alice introduces angular penalty loss to reserve margin between different classes. In our work, we discover the limitation of the activation function, ReLU. It should be noted that embeddings do not necessarily distribute uniformly across the entire unit hypersphere. The popular activation function ReLU is advantageous and widely used in many models. However, its output is always non-negative, which causes the elements of embeddings to be non-negative as well. This limitation means that the embeddings can only occupy a very small portion of the entire hypersphere space. For embedding vectors with d dimensions, they are only able to utilize 1 divided by 2 to the d's power of the entire space. This means a large portion of the hypersphere is unused, which may lead to a crowded space. Therefore, we adopt the odd-symmetric activation function tan. Unlike ReLU, which only non-negative values, the output of tan is distributed symmetrically on both sides of the origin. By using tan as the activation function, embeddings can be distributed over the entire hypersphere, thereby improving the sparsity of the feature space. To optimize the distribution of embeddings and achieve a clear separation between the features of base classes and future classes, it is necessary to adjust the embedding distribution within the entire hypersphere. This will ensure a greater distance between the prototypes of different classes, minimizing the overlap between their distributions. Specifically, we aim to distribute the embeddings of base classes in the upper hemisphere and those of future classes in the lower hemisphere. To achieve this, we set a base vector as a reference vector to differentiate between the upper and lower hemispheres. The similarity between a feature and the base vector determines whether the feature belongs to the upper or lower hemisphere. A positive similarity indicates the upper hemisphere and a negative similarity indicates the lower hemisphere. Then, to enforce the distribution of base classes in the upper hemisphere, a regularization term is used to maximize the similarity between base vector and base embeddings, where MB denotes the margin from the demarcation line of upper and lower hemisphere. For future classes, we utilize the generation of pseudo-samples, which can mimic the characteristics of the instances that the model may encounter in the future. Similarly, we calculate the similarity between pseudo-sample and the negative base vector and use the loss that constrains the distribution of the future classes in the lower hemisphere, where MP indicates the margin on the lower side of the upper and lower hemisphere dividing line. By assigning base session features and incremental session features to the upper and lower hemispheres of the hypersphere, respectively, we can identify the session of a given sample based on its similarity to the base vector, and thus predict its label more accurately. In cases where the similarity of a sample with the base vector is below 0, this indicates that the sample's feature distribution is located in the lower hemisphere of the hypersphere, which suggests that the sample is less likely to belong to the classes in the base session. Consequently, the confidence of the base class needs to be reduced to account for this. To summarize, our approach involves 3 loss functions. First, the cross-entropy loss is used to learn the base data. Second, the loss LB helps to distribute the embeddings of base classes in the upper hemisphere. Finally, the loss LP helps to reserve the lower hemisphere for future classes. Through this, embeddings can be distributed over the entire hypersphere, thereby improving the sparsity of the feature space, and specifying and reserving space for base and future classes reduces the overlap of different distributions. Here is the experiment result on CIFAR 100. And Mini Image Net, which shows our method achieves state-of-the-art performance. The ablation study shows each part of our method plays a crucial role in our learning paradigm. Besides, we analyze the effect of margin on feature distribution in our method. For different margins, the effect of LB on the distribution of features in base session is shown below. As the margin value in LB increases, the features tend to move closer to the base vector, specifically towards the upper pole of the hypersphere. With a small margin, the model's feature distribution becomes more compact due to the regularization effect, resulting in a reduced range of angle between embeddings and base vector. In conclusion, our main contributions include: we propose using an odd symmetric activation function instead of the commonly used ReLU, which allows for a more complete and sparse embedding space. And we allocate space for features of base and incremental classes, with the help of pseudo-instances generated by mixed base samples. Besides, during inference, we rectify the samples in the lower hemisphere, reducing their confidence in being predicted as base classes. In the future, we may focus on such topic, how to reserve most of the hypersphere for future classes, which would be more advantageous for model learning continually. And compared to ReLU, using TAN may cause problems such as gradient vanishing during the training process. Future work will include the seek of an odd symmetric activation function that combines the advantages of ReLU. Thank you for listening.